So there are two important limits that show up when you're trying to come up with the derivative of the sine function, and you either need to take them on faith or you need to see them proved. So the first limit that is important for the derivation of the derivative of the sine function is the limit as theta goes to 0 of sine theta over theta is equal to 1. And you can always look at the graph of sine theta over theta, which we've already done. And if we do that, we see that there's graphical evidence that as theta goes to 0 from the negative side and the positive side, in other words, as theta approaches 0, the function outputs seem to be approaching 1. So there's strong graphical evidence of it. But you can also prove it definitively by using the Squeeze Theorem. And to do it using the Squeeze Theorem, there's more than one way, but one possibility is to construct in quadrant 1 this picture right here. And here's what's going on in this picture. We have the area of this large outer sector of a circle. So the area of this big pie slice, if you want to think about it that way. So we'll call that the area of the large sector. And then you construct the area of this smaller sector. That's constructed by taking this point on the graph, which I'm working off of a unit circle. So from trigonometry, this is the ordered pair cosine theta sine theta on the unit circle, where theta is just the angle we make with the positive x-axis. So construct this smaller sector where we drop the perpendicular from the point we use to establish the large sector. We drop the perpendicular, and we get this ordered pair right here. And this is would be the ordered pair cosine theta 0. And then we construct the sector based off of that point. And so we're going to call that the area of we'll call it the small sector. And then what we do is construct a triangle. So the triangle's right here. And the idea is that this triangle has an area that's between the area of the small sector and the large sector. So the area of the triangle is between the area of the small sector and the large sector. So we wind up with this three-part inequality, which is what we did before when we used the Squeeze Theorem. We come up with two values between which we know our third value is always squeezed. And if we go ahead and do that, let's erase some of this mess. And we step out to GeoGebra for just a second. So I'm going to hit escape and keep those changes. So if we pop GeoGebra up, so here's GeoGebra Classic 5, web-based version. So I've got the outer blue circle, or outer blue sector. Here's the inner kind of maroonish triangle, and here's the small sector. And as we move in quadrant 1, we see that the area of that triangle remains between the area of the two sectors. And then theta is just the angle that we make with the positive x-axis. So if we let theta go to 0 from the positive direction, we see that they actually squeeze into the same area when we take the limit as theta goes to 0 from the positive side. So remember, in quadrant 1, theta is positive. In quadrant 4, if we rotate away from the positive x-axis, theta is negative. So we have this, we have these two areas, these two sector areas between which the triangle area is squeezed. And then we are going to need to replicate this picture, because in quadrant 1, if we let theta go towards the x-axis, theta is going to be positive. Theta is positive in quadrant 1. And then rotating to the x-axis, we would actually be taking the limit as theta goes towards 0 from the positive side. We're also going to need to take the limit as theta goes to 0 from the negative side. So it'll be a quadrant 4 approach. And we'll see that we need to tweak things a little bit if we're working in quadrant 4. So the idea is we can actually calculate the area of the two sectors and the triangle. So remember or recall from trigonometry that if you have a circle sector and it has an angle theta with respect to the positive x-axis, then to get the area of the circle, you use the fact that one full revolution is 2 pi radians, and you say, what fraction of 2 pi is theta? Well, it's theta over 2 pi radians. It's the fraction of a circle I've swept out. And then you just calculate the area of the full circle, pi r squared, multiplied by the fraction of the circle you've swept out. And if you do that, pi cancels, and you wind up with theta r squared over 2 is the area of a circle sector. So in the case of the larger sector, the radius is actually 1 because we're working on the unit circle. So we wind up with the area of the large sector just being theta over 2 times 1 squared is just theta over 2. There's the area of the large sector. The area of the small sector, so remember the ordered pairs here on the unit circle are cosine theta, sine theta. So down here, this ordered pair is the ordered pair cosine theta, and we're on the x-axis, so the y-coordinate is 0. So it turns out that this smaller sector has radius cosine theta. So we would replace the radius with the cosine of theta, and we would get that theta over 2 times the cosine squared of theta is the area of the smaller sector. And then you just need to work out what's the area of the triangle that's sitting there. Remember, triangle area is just 1/2 base times height, but the base of this triangle is 1 because we're on the unit circle, and the height, which you get by dropping the perpendicular from this point to the x-axis, the height of that is just the y-coordinate, sine theta. So we just wind up with sine theta over 2, sine theta over 2 as the area of that triangle. So the area of the triangle, sine theta over 2, is always between the area of the two sectors. And then we do need to take the limit as theta goes, as theta goes to 0 from the negative side as well, which means we would need to replicate the same picture, but replicate it in quadrant 4, because we're going to let theta come into the x-axis from the side, which means we're approaching 0 from the negative side. In quadrant 4, when we rotate away from or clockwise from the positive x-axis, remember from trigonometry that our angle values are negative. So if we replicate this picture in quadrant 4, here's what's going to change. Theta will be negative. Theta is negative. And down here, when we're looking at the sine function, which is showing up here, we want to remember that in quadrant 4, the sine of theta is going to be negative as well. So theta and sine are both negative in quadrant 4. So because we're calculating areas, what we would need to do is take the absolute value of theta so that we don't get a negative area. So that would be the tweak that you would make in quadrant 4. Okay. So then you could multiply through by 2, multiply this 3-part inequality through by 2, which would eliminate the 2's in the denominators. And then the next step is we could divide each term of this 3-part inequality by the absolute value of theta. So divide each of the 3 parts by the same thing. The absolute value of theta divided by the absolute value of theta is 1. So we get just the cosine squared of theta, less than or equal to here. Absolute value of theta divided by itself is going to be 1. And then what we want to recognize is that if we're in quadrant 1, the sign is positive and the absolute value is positive. So sine theta over theta would be positive in quadrant 1. And in quadrant 4, the sine and theta are simultaneously negative. So this ratio would always be positive. So we're able to drop the absolute value signs. And then we just take the limit of all 3 parts of the 3-part inequality. Take the limit as as theta goes to 0 of the cosine squared of theta is less than or equal to. Take the limit as h goes to 0 of sine theta over theta is less than or equal to the limit as h goes to 0 of 1. The domain of the cosine function is negative infinity to infinity. So by theorem, to calculate its limit, we can just plug the 0 in, which gives us cosine squared of 0 less than or equal to the limit we're looking for, which is the limit as, theta goes to 0 of sine theta over theta, less than or equal to, and the limit, this should be theta, this should be theta. The limit of a constant is just a constant, and the cosine of 0 is 1, so we get 1 squared is just 1. So we wind up with the limit that we're trying to calculate, which is the limit as theta goes to 0 of sine theta over theta. Because it's squeezed between 1 and 1, it has to equal 1. So the limit that we're after is 1 by the squeeze theorem.